Okay, let's start. Uh, so again, I have domain M in output domain with a smooth boundary, compact area. Equals 1. So we consider the motion of ideal incompressible fluid in this domain. U is velocity field. Is a U gradient of the stream function. No, let's take speed from the m equals 0. Yes, it seems that we can consider any number of holes, but it is not just for simplicity, just simply connected. Omega equals U equals Laplacian of psi. Yes, and energy of U equals 1/2 integral U squared dx equals integrate by parts minus 1/2 integral omega psi dx. Now mixing the results. The f x integral k x y fy dx, where first k x y non-negative measure integral k x y dx equals 1. Integral k x y dx y equals 1. The set of size k is denoted by P. P means polymorphisms. Then we say that omega 1 less than omega 2 if omega 1 equals k omega 2 for some k in our polymorphism. So they form a semi-group. P is a semi-group. Yes. So this is partial order. So U1, I write less than U2 if curl U1 is less than curl U2. Now V only suppose you have U V1 equals set of V such that V incompressible, the end is 0 on the boundary, and so V in L2. Yeah, V 0 equals, let's say, of V such that incompressible, the n on the n is 0, V in L2. So this time both this and this are in Greek sense. And given u in V1, then we define omega u equal, let's say, of W V1 such that W is in this sense, where is in this sense, less than U, and energy of W equals energy of U. Yeah. So omega U contains, if you start from U and run the Euler equation, solution of Euler equation, then for any t, positive t, the solution will be in this omega U. And even the weak limits of the solution for t growing goes to infinity, also in this set U. So let me write omega of U orbit of U in V1 under the Euler equation. Yeah, this omega of U with closure of one of for U. Yeah. So orbit and the closure. So any V in for U V in omega U.
Weak in L2.
Excuse me?
Weak in L2.
Weak in L2. Weak in V1, and of course strong in L2.
Okay.
Or weak, the what is this? Converge weak. Yeah, thank you. No, that's it. Minimal element. V in omega u is such that if w omega u and w is less than v, then v less than w. Yeah, no, every time we have partially ordered set, we define minimal element. No, or W is equivalent to this. No, so here I wrote last time, and now the nature of minimal element. On the what is a minimal element? No, first of all, then if say v less than u in this sense, then L2 normal curve v L2 less or equal L2 normal curve u. So this gives some material sense of what does it mean. So say omega 1 equals curve v, omega 2 is curve u. Omega 1 x is integral a x y u of y omega 2 dy. Yeah, where there exists that this way. Now, norm omega 1 and 2 squared equals integral integral a x y omega 2 of y d y squared dx. Yes, and now we can consider this is the following. Let us define k x y dy. This k is k x y is a positive measure. Yeah, non-negative measure such that its projection is just Lebesgue measure. So this means we have one of versions of Fubini theorem reads here follows equals mu x so or almost all x in M where exist measure or positive measure no x integral no x dx equals 1 such that who took my eraser?
The window.
Integral k x y omega 2 y dy equals integral omega 2 y d mu x y. Yes. And so sorry, A equals integral mod integral omega 2 y with no f of y square dx. Now here we can use the Schwarz inequality. It's less or equal than integral. Here integral omega 2 square of y dx of y dx which is equal now we use again we integrate with respect to x integral omega 2 square of y integral here we don't have x mu x dy. This integral equals 1. Yes. So this integral omega 2 square y dy equals norm omega 2 square. So omega 1, norm of omega 1 square after all this is less or equal than norm omega 2 square. Yeah. So let me put here this symbol. And no, it is natural that there is mixing operator. It's near the function, and this operation always results in decrease of norm. So it is natural. And now let us. I will keep it. And now if v less than u, say W, and W less than V, then there exists area preserving almost everywhere in vertical. E to M such that curl V equals curl U T minus 1. No, almost everywhere. Yes, so if no, I'm sorry. If V less than omega and norm curl V to equals norm curl W, norm curl W equal, then W less than V. I can write this way. No, let me not prove this fact. If you start, you will immediately do it yourself. Let me leave it as a problem. Yes. So to let me write. If V W and omega U and V lambda W, then there exists invertible a measure with the resolving my C and the M such that curl V equals curve U minus 1. Now the symmetric curve, W. Curve W equals curve V and C. No, again, it is true, but let me, it is maybe a little failure. So, okay, now let me go ahead. So, now theory. Suppose V is a minimum amount of only U. V equals psi, omega equals V. Well, just prefix notations. Then this monotone function. Monotone means either monotone increasing or monotone decreasing, or constant. It's also monotone. F such that omega equals F F of Laplacian psi equals F of psi. And this implies the following thing. Curve V is constant along every curve psi is constant. Yeah. Because it's simply curve V is a function of string function. Yeah, it's written here. But draw a picture. So this is a level line of string function. C equals C. Yeah. And the vorticity is constant along this line. Omega equals Q1, Q2. Yeah. But vorticity by the basic transport theory is transported by the flow itself. So the vorticity is transported along this line. But all the domain is related into such streamlines, yeah? And this means that vorticity is moving along the instantaneous flow lines, yeah? So this means that vorticity is stayed constant along the same line. Yeah. So this means that V is a stationary flow. V is a stationary flow. Yeah. And so again, we have this equation. This equation is more well known in different respects. Yeah. So it's related to different branches of mathematics, and in particular here. So what is this? This is a theorem. So it is not proved. Now I'm going to prove it. No, in fact, we have no, in some more general sense, a variational problem to find the minimal element, not with respect to the usual numerical order in the real numbers, but in some more interesting set with partial order. Yeah, in the for real valued variational problems, we would derive the Euler equations for the minimum. Yeah, Euler equation relate to necessary to one moment necessary condition of minimum. So if we have a point of minimum, then at this point the functional satisfies some sort of Euler equation. Yeah, here is exactly this, and in some sense, this relation is all of these relations play the role of the Euler equation. So I have to introduce some sort of variations. What is variation? In fact, in the variational calculus of variations, we have different sorts of small variation. What is small variation? Yes, if you consider, say, what is done in the control theory, in the maximum principle, there are also some variation, but are quite different sort than we use in ordinary analysis. Yeah, and so here we consider a small variation, namely the following. So omega is curl V. We consider a sort of local mixing. Local mixing. It is the following thing. How did I denote it? First, let us K in P. Yeah. Let us consider the following. K epsilon equals 1 minus epsilon identity plus epsilon K. Yeah. So this is also a mixing operator, because mixing operators, set of mixing operators is convex. Yeah, when epsilon is zero, it is identity or small. So it is first step, small mixing. And let us see what happens with the energy. Energy of very epsilon of V equals integral minus integral integral T omega dx equals minus integral, what is T delta minus 1 omega times omega dx. Yeah. Now here, delta omega, the change of omega, equals minus epsilon omega plus epsilon k omega. V plus delta V equals integral delta minus 1 omega plus delta omega times omega plus delta omega dx. Yes. It is equal to delta E equals integral delta minus 1 omega here 1/2 delta minus 1 omega times omega delta minus 1 omega times delta omega plus delta omega delta minus 1 delta omega omega times delta minus 1 delta omega times omega dx. Yes, so this is no plus quadratic term which I neglect. Equals integral 1/2 C на дельта омега plus дельта Пси на омега dx equals minus integral P somewhere is minus. Here is minus. Minus integral China delta omega dx plus higher order term. Now, what is delta omega? Equals omega minus omega. Yeah. Yes. Omega no times epsilon. No, epsilon is small. The E equals minus integral right? The omega minus omega dx. Yes. And now we are free to use to choose K. This is mixing. And so let us choose the following thing. Let us take 2 points, say point X and point Y. And around this point, this and this, let us choose a small disk of small radius. And let us write the omega of Z equals omega. Let us, this vector is H. H is y minus x. Z plus H. Z in, let's call M1, MX, and MY. MX. Omega Z minus H. Z is MY. One moment. So if X is here, X plus H is Y. Yes. And Z omega of Z otherwise. Yeah. So this means we take the function here and move it here. Take the function here, move it here, and did not change it beyond these two disks.
X and Y are two fixed points.
Excuse me?
X and Y are two fixed points.
X and Y are two fixed points, yes. Okay. So now what is delta omega? Delta omega of Z equals first, let me step by step. A epsilon omega of Z equals 1 minus epsilon omega of Z plus epsilon omega of Z plus H when Z in Mx. 1 minus epsilon omega of Z plus epsilon omega of Z minus H if Z in My. And omega of Z otherwise. Yeah. Now, what is the variation of omega? Delta omega of Z. So we have to subtract from this omega of Z equals epsilon omega Z plus A minus omega of Z. Mx epsilon omega of Z minus H minus omega of Z. Z and Y 0 otherwise. And now we have to why I am so interested in variation of energy. Because the condition to transformation, V belongs to our omega U, is that the energy is the same as energy of U. Energy of V should be the same. So variation of energy should be 0. Yeah. To keep it inside this. And so where our formula, delta E, which is delta omega. Delta E is epsilon integral minus epsilon integral over m t delta on dx equals minus epsilon integral over m t of z delta omega of z dz. Yeah. And now delta omega is 0 outside of these two small disks. Yeah. So equals, let me write integral over m x plus my of the same phi of v delta omega of v dz. And now let us look. Phi is inverse Laplacian of omega. Omega in A2, so phi in is H2. Phi is continuous. Delta omega is L2 function, but due to Lebesgue density theorem, for almost all the points, it has some definite value. Means if you take average over small disk, and then the radius of this goes to 0, then we have a limit of this, which is the canonical value of this L2 function there. Yeah. So this means that approximately we can approximate if we assume that phi is continuous and delta omega in our sense is almost everywhere continuous in this sense, which in sense of density theorem, we can say, right, that delta E is asymptotically when radius of this two small disk goes to 0, the following thing.
There is an epsilon missing, right?
Excuse me?
Yeah, there was an epsilon missing, right there. Yes, you wrote it. Yeah.
Yes, I'm sorry. Delta E is C of x delta omega of x minus psi of y delta omega of y. Yeah. Equals no with the infinitesimal epsilon e r square. Yes, like this. Which is equal phi of x. And what delta omega of x? It is omega of y minus omega of x. Plus plus or minus no, here should be plus, of course. Should be plus. So plus C of y. Here, omega of x minus omega of y, because we are at the point y. Or omega of x minus omega of y. And finally, it is psi of x minus psi of y, omega of x minus omega of y. Yeah. So this is this variation of kinetic energy. And now, why I am doing all this? Because the following thing. What can be said about the sign of this variation of energy? So if for some, let me denote the delta xy. So this is variation of energy, which is related to these 2 points, x and y, where we do this small variation. Yes. Now, if for some x1, y1, delta for the term x1, y1 e more than 0, and for some x2, y2, delta x2, y2 e less than 0, then what? Then we can have some convex combination of these two variations. For some convex combination, here, let me write here k x y. Say 1 minus a k x1 y1 plus a k x2 y2 of mixings. Delta E equals 0. Okay. Yeah. So, for example, for these two, this variation is positive, and say for these two, it is negative. Yeah. Then we take with some coefficient this mixing plus some with a coefficient complementary coefficient this mixing complementary to 1. It is a convex combination. It will be again a mixing operator, and so we have some mixing such that it does not change the energy on one hand. On the other hand, it is a true mixing. Yes, real mixing. This means that it decreases the L2 norm of vorticity of omega due to the lemma which I started from. Yeah. So this means that V is not minimal. Minimal element of omega u. It is not minimal element of omega u. So now, okay. You know what? I have a paper where it is all written maybe in a little more detail. So you can look there. I will give you coordinates. B is minimal. Remember, on review, when either C x minus C y omega x minus omega y more equal than 0 or C x minus C y omega x minus omega y less or equal than 0 for any for almost all x, y, h, and well, this is what plays the role of the Euler equation. Euler equation means in the sense of variational problem. Our conclusion. Now, how can we extract here this relation that Laplacian, that omega is a monotone function of psi. So if say omega in L2, psi in H2 0. 0 means 0 dash condition on the boundary. And psi x minus psi y omega x minus omega y more or equal than 0 for all x, y, and m, then there exists monotone growing, let us say, non-decreasing function f such that omega of x is f of psi of x. Yeah, no, I don't need here that omega is Laplacian of psi is omega. Simply two functions such that there is relation. Is it obvious? No, not at all. No, okay. So let us consider here the following function. Define g that equals sine of x plus uh, omega of x. So note how to argue if x y in n and psi x more than psi of y, then by this relation and suppose psi of x minus psi of y omega x minus omega y equal to 0. If x, y in M and the following thing, psi of x more than psi of y, then no, by this relation, by this inequality, omega of x more equal than omega of y. Yes, the difference should have the same. And then g of x more than g of y. Uh, uh, and g of x equals g of y. Then suppose. Then the following, if t of x more than t of y, then omega of x more equal than omega of y. And so g of x more than g of y. So if c of x more than c of y, then g of x more than g of y. If no, symmetrically. If P of y more than C of x, then G of y more than G of x. Hence, C of x equal to C of x. So other cases are excluded. The same reasoning shows that omega x is equal omega of what? G of x equals G of yes. No, if G of x equals G of y, then psi of x equals psi of y, and omega of x equals omega of y, means that hence psi depends on G. Omega that is the function of G. And the function G omega G are monotonic, non-decreasing. So the functions are monotonic, non-decreasing. We proved it. And now why I took G? Because since the function psi, right? Psi in H2, psi in C1 minus epsilon, yes? This means it is a continuous function, so its range covers some interval in the vertical axis, yeah? G of M is C minus C plus. Yeah. Because C is
Psi of n. Psi of n or G. What do you want to?
Psi of G of M, like this. Because yes, psi of M. It is an interval, yeah, and so this means that we can consider the inverse function, inverse to this continuous function on this interval. Yes, so psi minus 1 psi minus psi plus 2 R, but psi is continuous function, so it is bounded, yes, to AB. Yes. And so we can write that omega psi is psi of G. G equals psi minus 1. Wait. Where is psi of G? Let me write omega of G. Psi minus 1. Psi. And omega equals omega psi minus 1 of psi equals f psi. Oh.
Sorry, you're using a small psi and a big psi, right?
Because it is small psi,
Yeah.
this is small psi is a function in M,
Yes.
and the large psi is function in the segment.
Okay.
Yeah. No, similarly, if psi x minus psi y omega x minus omega y less or equal than 0, yes, then we use the function h equal psi minus omega. Instead of psi plus omega, h equals minus omega of x. Yeah. And then the same reasoning goes. Okay. Now I want to introduce some classification. Minimal. I call it the minimal flows. So we have three classes of these flows. First class, when psi x minus psi of y, omega x minus omega of y, more equal than 0. What does it mean? It means that if you take this flow and try to mix further its vorticity, the energy will grow because it is the variation of energy with the small, after the small mixing. Yeah. So the energy will grow. So I call them energy deficient. volts. Second, the same Cx minus C1 omega x minus omega y is less equal than 0. Then for a no energy, no, it is in decrease, so energy excessive. Energy excess, they have too much energy, and any further mixing decreases the energy. If it is less than, so any small mixing, no. No, it is energy deficient. Energy deficient. In a few minutes, I will give you examples. You will see. And these are energy accession. So they keep so much energy that any further mixing or vorticity decreases the energy. Yeah. And the first is where omega of x is just constant. Yes, which are called, no, okay. Energy network. Flow. After constant, just only one such flow. No, consider examples. Yeah, and the theory, which is simple, but let me skip its proof, is the following. For u v1 of minimal elements under u belong to one class. So we have three classes of minimal elements, and all minimal elements belong to one class. So it is not the property of particular minimal element, it's the property of U. So examples. We have two sources of examples at hand. It is the parallel flow in a strip in the channel with some profile, and circular flows in a disk. Yeah, so let's start from parallel flows.
So I have a question.
Excuse me?
I have a question. When you say this, let's say now you know that all the minimal elements
Once again.
now you know that all the minimal elements belongs to one
So one of these three classes.
of these three classes,
Yeah.
right? So you are, do you expect the 1 and 2 they happen both generically?
Of what?
1 and 2.
Yes.
Is one of them favored by the system?
No, one or two, but not both.
Depending on you.
Depending on you. So you itself can have too much energy, too little energy for its stock of vorticity, or it has exactly amount of energy to have just one minimal element, which is flow with constant vorticity.
Now, if I'm saying if I pick a random U, let's say I look at torus, I pick up random U, so there is no idea to determine whether they are one or two, or one of them is favored for.
No, we have idea. Okay, of course, you have idea. You take the average vorticity,
Mhm.
yes, a constant, and compare this flow with this constant vorticity and the flow u, depending on relation of the energies.
Okay.
Yes,
Mhm.
so yes, just in one simple operation,
Mhm.
and you will know. Yeah. So consider the flows in a parallel stream. Our domain, it is a channel with periodic channel. Or if you wish, it is a flow on the surface of cylinder. Yeah, this is not simply connected domain, of course. Yeah, so we have to perform a little more to take into account all components of the boundary. Result is the same, but no, it will require a few more minutes to explain it. So, but the result is the same. So parallel flow u equals say f of y, and no, it is u of y 0. So velocity is along the axis of this strip, and you have some profile. For example, this profile. Or so first of all, this is a stationary flow. The stream function of this flow is psi. So you have to integrate it of x2. Let's say if it is parabolic equals x2 cube plus a x2. The stream function. No, this stream function is in general non-zero on the boundary. No, why even those b x2 square? If it is not, it can be not symmetric. Yes, and it can be even not parabolic, but any convex function. So u of x2 convex function. Oh, let us consider the case a b equals 0 to be sure. u x2 equals x2 cubed. Yeah. Then x2 square, 1/3 psi x2 equals x2 cube, omega x2 equals 6 x2. We can consider say -1 x2 from -1 to 1. Yes. Then here we have some energy. We have to integrate the square of this from -1 to 1. It is energy. Here, definitely more than 0. But if we say mix vorticity, which is 6x2, yes, take average from x2 -1 to 1, then it is 0. So following what I just told, this means that any mixing of this profile of this flow, any mixing will decrease its energy. So it is energy sense. Now what is energy depletion? If you x2, say x2 cube, yeah, then psi x2 equals 1/4 x2 4, and omega x2 equals 3 x2 squared. And if you take the average of this vorticity, then you have the energy will increase. Yeah. No, we can take better to some power to n+1, for example, to have it more expressive. Then the velocity profile will be like this. Yeah. So we have vorticity, which is approximately delta function here and here. If we say smear it a little, it is positive, the same sign, then we'll have something like this. And so the energy clearly grows. No, you can substitute it into the variation of energy under small mixing, and you will see immediately that for this profile, the energy increases when we mix it. Yeah, so this is energy depletion. And the last cause is when vorticity is constant. U of x2 equals x2, omega equals 1. Yes. Now, if omega is constant function, however you mix it, it doesn't change it. So do not change the function, do not change what is the energy. So it is not okay. Energy net. Now these pictures are, I think, familiar to many of you because these are the classes of Arnold stable flows. Arnold, formally the stability, the spectral stability of these flows was established much earlier by Rayleigh. Rayleigh found that the flow with convex profile is linearly, not linearly, spectrally stable. There is no unstable, say, solutions of linearized equation, no exponentially growing perturbations. This is a new class. I don't know who discovered, maybe I'm not, maybe somebody before him, and this is trivially stable. So this way we find that these solutions are, have some fluid dynamical meaning. They are stable, means they have no potential for further development. I think stability is the top stability is just gone, it's just death. Now let me consider the general question. Suppose you have arbitrary initial velocity in two-dimensional domain, and the fluid is moving, governed by the Euler equations, and we wonder what will happen in a long time. Yeah, a very long time. So the vorticity is carried by the fluid. It is mixing, and the natural conjecture is that this mixing can be stopped only if you meet some obstacle. Yes, no, the obstacle can be, for example, some conservation law. Here it was the energy conservation. Yeah. By the way, in the case of channel flow or flow in disk, we have also conservation of momentum and of angular momentum, and they bring us some more general classes. Say, in case of the flow inside the disk, we have, say, vortex patch, which is moving without change of its shape along the circle. Yes, so these things also can happen. But is it? But this solution is obtained by the same procedure. Only you have to change your a little bit generalize your reasoning, and you will have this also. But it is so extension, but not very far extension of this class. If our domain have no such symmetry, arbitrary domain, then the question arises what happens here. So the first hypothesis is that here nothing can stop our fluid from mixing its vorticity to the end. The end is when parallel mixing becomes impossible. I think that this is beyond our imagination to imagine what happens here. But it is the scope of computer simulation. Yes. So this now with this spectral method, it becomes quite available. And in particular, even myself with my very small and weak computer skills, I also made such simulations and found that no, there is no tendency to this complete mixing. And as a result, you have a lot of interesting flows, which are definitely not minimal flows. Yes, so we don't reach the bottom in this case. So something stops us. So what is that new obstacle which can stop us and which does not reduce to some known conservation law? Such obstacles is in other situations, such obstacle is if we have some attractor. But here, how can we have attractor if it is a conservative system without friction? So it is what I'm going to discuss next time. So the next result, next set of results is what happens really, that we really meet attractor, which does not permit us to reach this bottom, this minimal flow, and what it is, and I will discuss it next time. So now let me finish. And you know what? This is my paper about this, and I think it can be easily found in internet. Let me write its title. It's uh, Yes, you can find, I think you easily find it in the internet. The paper which contains all this and a little more.